let's start our new lecture. Okay, now we're recording the lecture. Let's see what's the easiest way to solve such a problem. Okay. So this lecture is about our second chapter of our textbook. Let's take a look at this example. Now you have a charge, which is Q, and it's located at X. And at the origin, there is a wall or there is a conductor, which is perpendicular with X-axis. Let's say it's in Y-axis. And this conductor is grounded so that the phi or the potential on the surface and inside the conductor should be 0. Now the question is, if you have such a system, you have a Q and you have conductor, what's the electric field at any point? Let's say this point, which is R from origin. And R is a vector, of course. I want to calculate E here. So first of all, what does the electric field line look like in such a system? Let's say, let's draw a picture here to illustrate the field lines. Pen. I'll draw a new picture, which is a conductor and charge Q. Intuitively, what does the field line look like? Let's say if this is a positive charge, it should be something, it's a positive charge, so you know the potential here is positive. And the potential at this conductor surface is 0. Then you know the field lines go from here to there. Okay, this is a conductor. Let's make it bigger. Big conductor. So first, be careful. Take a look at the field lines. First of all, does the field line look like correct? Is it possible? Does this distribution of the field line possible for a conductor? Yes or no? Yes. Okay. Partially right. So here, for those center lines, it's correct. But if we take a look at the lines further away, is it possible on the surface of a conductor? Think about what we have learned in the last class. We have learned something about we have learned about the field lines at the surface and inside a conductor. So first of all, in a conductor, what's the direction of the field lines? Let me remind you a little bit. Now, if you have a conductor, a spherical conductor, and then you have a charge Q outside, what's the field line inside the conductor? Zero. No field lines. Why? Can you explain?
Because like
Yeah, it will cancel out. Or in another way, if there is a field line inside, what happens? It's a conductor. If there's a field line in the conductor, conductor means the charge in the material is free. They are free. If there are some field lines inside, what happens? The charge will move, right? The positive charge will move to this side and negative charge move to the other side. Finally, when it's in an equilibrium state, means no charge is moving. That means inside the conductor, there shouldn't be any field lines. There's no electric field. Otherwise, the charge will move. There will be a current in the conductor, right? This is what we have learned in last class, if you remind yourself. So it's the first thing. The second thing is, let me erase some of the drawings. Option. Second, on the surface of a conductor, is it possible the field lines look like this, or the field lines have some tangent component? Is it possible? Why? Right. So if there's a tangent component for the electric field, the charge on the surface will move. The charge doesn't move, or when it's in an equilibrium state, simply means there's no tangent component of the electric field at the surface. So the field lines should always be perpendicular to the surface of conductor if there is any field lines. Does that make sense? Because if it's not, it will induce some charges. And those charges will move to some places, and then finally, when it's in equilibrium state, it makes sure no charges are moving, means all the field lines on the surface of the conductor are perpendicular to the surface. And there shouldn't be any electric field lines inside the surface. If it's a conductor, of course. If it's not a conductor, then the charges are not really moving, then the conclusion are completely different. But here, for conductors, we know the field lines at the surface must be perpendicular. Then let's go back to our original question. Is it possible the field lines distribute like that? No. Let's redraw it. First, I'll erase some of the impossible field lines. This is impossible. What happens? Doesn't work. Oh, no. Oh, okay. Let's try it again. So in this case, you have conductor. Let's say this is your conductor and this is your charge. Then the field lines should always be in this way. At the surface, it's always perpendicular to the surface. Something like that. Does that make sense? Okay, so now the problem is that what happens here if you want to calculate, let's say this is a region in x direction. This is a region. The distance between a region and the testing point is r, and of course r is a vector. Then how to calculate the electric field at this position? And we know when it's a conductor, this is a positive charge. It will gather some negative charges on this side. And on the other side, it will have some positive charges. This is induced charge. So that finally it makes your field lines in this way. It bend to be perpendicular facing the conductor at the surface. However, it's very complicated to calculate the induced charge. If you can calculate the induced charge, then if you know the charge distribution, of course, you can calculate the electric field here by using the superposition principle. Just simply use a lot of Coulombic equations, sum them up, you'll get the electric field here. Is there an easier way to solve such a problem? So what's the way? We can model this system with a different charge distribution. This is what we need to learn in today's class. It's called, let me first hide this thing. It's called the method of images. So here, when you have such a system, a Q, close to the surface of conductor, it equals to a system which is a charge without the conductor. Instead, you have another charge at the other side of your x coordinates. Let's say this is x. This is your origin. If you put an image charge, which is negative, which is in the opposite sign to your original charge, but has the same magnitude, what happens? What does the field line look like? First of all, it looks like, sorry, I'm using the touchpad to, I always forget to bring my mouse, so I'm using the touchpad. It's difficult to draw the pictures. So the field line will distributed look like that. And of course, field lines distributed in that way. Okay. Now, if you compare the system with a charge and a conductor and system with charge and negative charge, you figure out the charge distribution is exact, the electric field line distribution is exactly the same. So in this symmetric system, those field lines at this plane should always, at the middle plane, should always perpendicular to the middle plane, right? It has to be, so because of the symmetry. And then at this middle plane, what's the phi? What's the potential? It should be 0, right? Because it's a symmetry charge distribution. On the right side, it's positive. On the other side, it's negative. So in the middle, the uh, the potential should be 0. And then on the very far away right side, when it's infinitely far away, should also be 0. But in the middle plane, it's also 0. Then if you consider the field lines in the original question, and the symmetric image charge distribution system, you figure out when x is greater than 0, which means when we're talking about on the right side of the origin, then the charge, the field line distribution should be exactly the same. Does that make sense? So this is the way of using the charge of image charge, or the method of images. And this charge is called, let's say, image charge. And then, of course, on the right side, this method cannot do anything good. For example, on the right side, the electric field should be 0 inside the conductor in the original question, right? In the original question, it's conductor on the right side. So phi is 0, field lines is 0. But in this case, of course, on the right side of the original point, phi is non-zero, it's negative. And field lines is non-zero, it's going to the left. So using this method, you can successfully calculate the potential, field lines, everything the same as the original question, but on the one side, in this case, on the right side of the conductor. On the left side, it's completely different. But in a lot of cases, we only care about one side of such a system. Then using this method is perfectly solving the problem. So now things get very easy. If we ask a question, what is the electric potential here? Then how to do the calculation? First, you calculate the E based on Q. And then calculate the E based on negative Q. If you consider the entire system is just two charges system, negative charge and positive charge, you can calculate the electric field generated by each of the charges individually. Then you will get E1, E2, and then sum them up by using the vector sum. You will have something like this. That's the vector sum. Okay, so this is the concept of method of images. Using some tricks by position a single or multiple charges or imaginary charges in the system, you can replace the conductor and the induced charges just by simple imaginary charges, which can completely change the way of your problem solving. It can make your method of solving the question to be very easy. Now let's see the second case. A point charge in the presence of a grounded conducting sphere. Now this is a conducting sphere. Let's say it's grounded, which means the surface of the conductor is 0 for electric potential. For electric potential, if it's a 0 and you have a charge which is Q, and it's located at y. Let's say this length is y, and we, of course, we keep the center of the sphere to be the origin. Then how to calculate the electric field at arbitrary position P? And let's say the vector from origin to position P can be called X. So first of all, let's make a picture of this sphere. Let's say this is Y, and here is Q. And the distance is Y. What's the charge distribution? Oh, sorry, what's the electric field distribution? And the field line, again, should be perpendicular to the surface of the conductor of the sphere. The same reason, if it's not perpendicular, then the charge moves. When the charges move and equilibrium, it has to be perpendicular. Otherwise, it continues to move. So in this case, if you calculate the electric field, let's say at this position, P, it seems like very complicated. However, this problem can also be simplified to an imaginary charge problem. Now let's remove the conductor, remove the sphere. Instead, if we put a charge here, let's say this is a positive charge, and if we put a negative charge here, it can also generate a field line, which is in this distribution, positive, negative. So the entire effect of the spherical conductor can be replaced by a single charge, or maybe multiple charge. Let's say a single, if there is a solution, let's say it's a single charge, and let's see if there is a solution for a single charge to do the same thing. Then if you have a single charge here, you will get the electric field distribution shown in this way. Okay, let's say if there is such a charge, then this charge should do something, should have some electrostatic potential at the surface of the sphere, but there's no sphere anymore, no physical sphere. Let's think about a Gaussian sphere, Gaussian surface. If there's a sphere here, the potential should be 0. If the potential is 0, in this case, then what kind of charge will make it? Will make the potential at this surface to be 0. So first of all, let's say this is x. X is a vector. So x means the position of a point. If we want to calculate the phi, or the potential at position x or vector x, then we can use the Coulomb's equation. So it's Q over, first of all, the potential is generated by Q and another, let's say Q prime here. The Q prime, we know it should be a negative charge if Q is positive charge. Let's say Q prime is here and Q is here. We want to calculate potential at here at position P, or the vector from origin to the position P is X. Then what we can do is, first we calculate the potential generated by Q, and then we calculate the potential generated by Q prime. Then sum them up, you will get the final potential at this point. the reason you can sum them is, again, the principle of superposition. Okay, so suppose now you have two charges, you want to calculate the phi. So the phi generated by Q is Q over, so here it's a Y, so Y subtracted by, or X subtracted by Y, which is distance between P and Q. So Q over their distance, and then over 4 pi epsilon, which is a constant. And then for the phi generated by Q prime, it's the distance between X and the Y prime, which is the position of Q and position of P, and then Q prime over them and over 4 pi epsilon. So by using these two Coulombic equations, you can calculate the sum of the phi. And we want to make sure, let's say at the surface, a Gaussian surface or imaginary surface, at this sphere, on the sphere surface, the phi is always 0. And let's define the radius of the sphere to be a. From origin to the distance of a, that's the surface. And then at the surface, the phi should be 0, which means when x equals to a, the phi should be 0. X equals to a means on the surface of the sphere, right? Okay, now let's substitute x to be a here. When x equals to a, you can get here a minus y and a minus y prime. But let's take one more step. Let's try to choose q prime and y prime so that the potential is 0 when x equals to a. And let's define n is a unit vector in the direction of x, and n prime is unit vector in y direction. So x can be right in this direction. It's x n, and y, the vector y could be written in this form. It's a scalar y times n prime. The same thing for here, x and y prime. Then let's say if x equals to a, then you will get a times n subtracted by y n prime, a times n subtracted by y prime n prime. And for this left side, left term, let's take out a. If we take out a, then you get what inside the bracket is n subtracted by y over a when you take out the a. And here, if you take out y prime, you'll get the equation here. And then next step is there might be a lot of solutions to make the phi to be 0 when x equals to a. There might be more than one solution, but the easiest solution we can get for y prime, and where's q prime? Q prime is here. When q over a equals to negative q prime over y prime, let's say q over a equals to q prime over y prime, which is here. If here over here equals negative there, plus y over a equals to a over y prime, here is y over a and here is A over Y prime. If Z equals to each other, I'll use a square rectangle to highlight this term. If the circle equals to circle, circle equals to negative circle, and the rectangular equals to the rectangular, of course, it will be 0, right? This is one easily observed solution for this equation. And then this is the circle, circle, rectangular, rectangular. By solving this equation, in this equation, you have two unknowns, Q prime and Y prime. All the others are known. And then you can solve the problem to be Q prime equals to negative A over Y Q, Y prime equals to this equation. And then that's the solution. That's one solution. That means if you have another charge, the charge Q prime equals to A over Y Q and negative. And if you put it in the distance of A squared over Y, then the potential on the surface of the sphere will be 0, which means you can use such a charge, Q prime, and put it at the distance of Y prime. Then you get this imaginary charge to be taken care, or to be a substitution of the entire spherical conductor. Okay, so once you have the imaginary charge and the origin charge, then you can calculate E and phi, electric field and the potential anywhere outside the conductor. Inside the conductor, of course, the answer will be wrong, which is similar to previous example. Inside the conductor, in the real conductor, the electric field should be 0. But in the imaginary system, in the circle, the electric field is non-zero, it's negative. So inside the conductor, the imaginary charge cannot help at all. But outside, it's a perfect, easy solution. Okay, and then once you know Q prime and Y prime, the image charge is found, and then you can calculate the charge density induced on the surface by using epsilon, negative epsilon times the partial phi over partial x. And then you can get this distribution of the induced charge distribution. If you want to calculate the force, that's also easily to be calculated, because now you have two charges, one real charge, one imaginary charge. Remove the conductor, keep the charge and the imaginary charge. When you do a force calculation using the Coulomb's law, to calculate the force generated by the real charge and then imaginary charge, sum them up together, you get the net force, which is exactly the same as the system with one charge and one conductor. So the force could be written in this equation. Okay. This is what we want to introduce in this class. Let's go through a very basic example. Actually, two examples here. So first of all, when you have charge and conductors, the electric field lines will be distributed in this way. And then you can replace the conductor by a negative charge, the electric field line distributed in this way. On the right side of the system, it's exactly the same in figure 19 and 20. So when x is greater than 0, or on the right side, you can use this method to do the solution, but on the left side, you cannot do it because on the left side, in real case, the electric field line is 0. Then if you want to calculate a potential at the position here, let's say this is x, y, v, x, y, z. Forgive my writing because I'm using the touchpad. It's really difficult. Now, if you want to calculate the potential at x, y, z, what can you do? So here, this is r squared, q over r squared plus q over r prime squared. Let's say from here to here it's r, from here to there it's r prime. Then you can simply use the Coulomb's equation to calculate phi 1, phi 2, sum them up together, you get the final answer of phi. And here, let's see, this is phi. If you want to calculate E, you can use partial phi over partial x, or you can simply use Coulombic equation. But use it twice, one for Q, one for negative Q, sum them up, you'll get the equation here. If you want to calculate the induced charge, it equals to Ex times epsilon, and you know E at any position, so that you can calculate the E at x equal to 0, and you plug in the E times epsilon, you'll get the charge distribution, which is, of course, the surface density of the charge. In last class, we have introduced E on the conductor. E equals to do you remember eta, which is the charge density? That's a surface density on the surface of a conductor over epsilon. If you remember, this is what we have learned in a previous lecture. Then you can convert it into, sorry, here it used sigma, it didn't use eta. Let's say eta. It's a surface charge density equals to, of course, E times epsilon 0. So the same thing. And for induced charge, you can do integral of eta, or here sigma dy dz, and then after a calculation, you will figure out the induced charge on the whole plane, which is a conductor, is negative Q. And force can also be calculated by using Coulomb's equation. Sum them up. Another example is the spherical conductor and the point charge outside it. If you have positive charge here, the charge distribution, sorry, the field line distribution will be something like that. It equals to you withdraw or you remove the conductor. Instead, you put a negative charge at some position. At that certain position, the system will generate a field line in the same way. It's always perpendicular to the imaginary surface now. And on the potential, it's always 0. And we have derived the equation how to calculate the position and the charge of Q. once you have the q prime and the y prime or r prime, then you can calculate phi. Just use Olympics equation twice and then do the sum. Okay, that's all for today. But before we finish our lecture, let me ask a question. Let's say you have a charge here, you have sphere here. If I remove the charge, sorry, not remove, but if I move the charge, if we move the charge further away, then what about the imaginary charge? Will the imaginary charge be further away here, or it will be closer here? Think about it. Why?
I think because now it's further, so the electric field lines have more time in some sense to go up and then go down. So they reach the sphere with a smaller angle. So that would make the other charge to be closer.
Okay, it's a. Can you draw a picture? Show us your idea. You can use either blackboard, that one or this one. Either one is good. Okay, that's a very interesting solution.
Yes, I was thinking because it's here. For example, this one has some distance right here, but if it's further away, well, like we have more space, so we go up in a sense or down, and then we have more time to get closer, and so this angle could be different, meaning it would be closer.
Okay, great. So that's a way of, let's say, it's a pictured way, or intuitively you can draw some pictures and try to understand it. Another way is quantitative way, because we have calculated the distance here. It's r squared over d. So when d is getting greater, what about x? It's getting closer, right? So if the sphere is the same, when d is greater than x get smaller. Let's say if this is a region, if you move the d to the right, then the charge will move to the closer to your origin. It will move to the left. Is that what you expected in your picture? Exactly. That's actually in our textbook, it also discussed this effect. Let me see. No, it didn't discuss, but you already get the equation here. In our textbook, we use y prime. So when your y is longer, so this is the origin, this is your y. When y is longer, your y prime is shorter, which means it's closer to the origin, means it's getting to the left side. Okay, great. So do you have any questions? If no questions, that's it for today's class. I will stop and share the video via YouTube.